Assalamualaikum and hello everyone. Now we are going to continue our lesson on chapter 5, PN homojunction qualitative analysis, focusing on the Venn diagram under bias. In the previous video, we have learned the basic of PN junction Venn diagram at equilibrium. We have been introduced to the concept of transition region or space charge region or depletion region to describe the characteristics of PN junction. We have discussed on the Venn diagram characteristics that covers the consistency of Fermi level throughout the system, the carrier movements, the electric field and built-in voltage, and also the resulting four types of currents. We have also touched on the one-sided junction. In this video, we will continue our discussions on the Venn diagram of PN junction under applied bias. First, let us define the type of biasing methods. We have forward bias and reverse bias. Forward bias is when we connect positive supply to the P side and negative supply to the N side. Reverse bias is the opposite. That is when we connect negative supply to the P side and positive supply to the N side. And finally, we must remember that there are three regions exist in the PN junction: the neutral, P-type and N-type regions, and also the transition region. We must also take note that at the transition region, since electric field exists even without any bias, there are no mobile carrier in the transition region, or it is called depletion region. Thus, resistance at the transition region is high. This results in all of the applied voltage dropped across the transition region. Let's take a look at reverse bias. So what happened to the Venn diagram under reverse bias? For reverse bias, the P side is connected to the negative and N side to the positive. When this happens, the electrons at P side will receive more energy, thus the energy of the P side will increase and the Venn diagram at P side will move upward. On the other hand, when N side is connected to the positive bias, this will lower the electrons' energy on the N side and thus the Venn diagram on this side will move downward. This will result in a stretch of the Venn diagram, which will increase the potential barrier, makes the junction width wider, and increase the electric field. So, the resulting Venn diagram of PN junction under reverse bias is shown here. At this figure, the solid line is the Venn diagram under equilibrium, and the Venn diagram under reverse bias is drawn in the dotted lines. We can see clearly the differences where the potential barrier or the junction voltage Vj is increased when the PN junction is under reverse bias. The junction width also becomes wider and the electric field becomes larger. When the electric field increased, more carriers are swept away from the transition region. And when more electrons and holes were swept away, the junction width becomes wider. As for the junction voltage, Vj, general equation is given as Vj equals to Vbi minus Va. Thus, for reverse bias, Va is a negative value. The equation becomes Vbi minus negative Va. Thus, it becomes Vbi plus Va, which shows that it is increased. Take note that at equilibrium, there is no applied bias. Thus, Va equals to 0, meaning that Vj is equal to Vbi. Let's move on to forward bias. For forward bias, everything is the opposite of the reverse bias. The P side is connected to the positive, thus will lower the potential energy for the electrons, making the Venn diagram moves downward. The N side, connected to the negative, will increase the potential energy for the electrons, which makes the Venn diagram move upwards. This will make the potential barrier lower, the junction width narrower, and smaller electric field. The differences of the Venn diagrams under equilibrium and forward bias are shown in this figure. The dotted lines are the Venn diagram under forward bias and the solid lines are those under equilibrium. We can see that the potential barrier is smaller under forward bias and the junction width decreases. Since the electric field at the transition region reduced, less carriers are swept away from the depletion region, thus the junction width is reduced. And from the general equation of the junction voltage, since Va is positive value, we can see that under forward bias, Vj is smaller than Vbi, which means that the potential barrier is reduced. These figures are just to show you guys the differences that you should take note of the band diagrams at equilibrium and other bias. Comparing to the equilibrium, the reverse bias will increase the potential barrier and junction width, but forward bias will reduce the potential barrier and decrease the junction width. The electric field under reverse bias is larger and electric field under forward bias is smaller. So that's the end of our video for today. This is the summary of what we have discussed. When discussing the changes, you should focus on the potential barrier or junction voltage, the electric field, and also the junction width. And don't forget to ask any questions if you have any through our WhatsApp or FB. Good luck!